So now we're going to just go through the rest of the questions that we're going to need for this afternoon's prac. So we've defined what oxidation and reduction are. And the second question is, when a metal reacts with an acid, what is oxidized and what is reduced in the reaction? So when a metal reacts with an acid, we went through this yesterday. In year 10, there's some standard rules for, there's acid plus base gives salt plus water, acid plus carbonate gives salt plus water plus carbon dioxide. Do you know these rules? You need to know them. And then there's acid plus metal gives, what is it? This is year 10 work. Acid plus metal gives no, salt. Always the salt seems to be formed, plus hydrogen. Remember we were talking about this yesterday? Hydrogen. So in this sort of reaction, we want to know what is oxidized and what is reduced. So we could just use an example. Let's use an example. Let's use magnesium metal being added to hydrochloric acid. According to this, we're going to get hydrogen gas. And if you put your hand over the hydrogen, you can see the salt. Because a salt, the definition of a salt is a metal and a non-metal together. What is the salt that's going to be formed?
Magnesium chloride.
Very good. Magnesium chloride. And you need to then check the formula. Is that the right formula for magnesium chloride?
No.
Because it's unbalanced.
Two chlorines. Very good. Plus 2. How do you know? Periodic table. I showed you that yesterday. The valence. See, it's in group 2. Plus 2. That's in group 7. Minus 1. We need 2 of these to balance that out. So it's a 2. And then we need to balance the whole of the equation. So we put a 2 here. 2 chlorines, 2 chlorines, 2 hydrogens, 2 hydrogens. It's a plus there. So that's an overall balanced chemical equation, a complete one. We want to write the half equation so we can see what is being oxidized and what is being reduced. So we need to know which one is losing electrons. If I write magnesium down, this is what you could do. And then you draw an arrow and then you think, I just want to concentrate on magnesium. You write it as its ion. What is it going to be written as?
Mg2 plus.
Mg2 plus, very good. Mg2 plus, remember that's just shorthand, it's actually ions floating around in solution, aqueous. Now, we need to balance the equation. We've got one magnesium on each side, but the charges aren't balanced, so we've got to add electrons to the side that makes them both the same. So this is 0, no charge. This is plus 2. What are we going to add?
2 electrons to this.
Yes, 2 electrons. And once you've done that, you say to yourself, magnesium is losing or gaining electrons? Losing them. And so this is a... Yes, oxidation. Very good. You're very fast, you guys. Oxidation half reaction. Oxidation half reaction. And we need to work out what is gaining those electrons. I can see straight away that that's got no charge. So we're going to just write the hydrogen down for the gas. And then we're only concentrating. You can see chlorine's just a spectator. It's ions here and it's ions here. So we're going to write this down. And now we need to balance the charge on both sides. What side do I need to add the electrons to make sure it's balanced? This side, very good. And is it losing or gaining electrons?
Gaining.
Gaining, yes. Therefore it is a reduction half reaction, written like this. So we can now answer that question number 2. When a metal reacts with an acid, and this was just an example, what is oxidized and what is reduced in the reaction? What are you going to say in answer to that question?
The metal is oxidized.
Yes.
Oh,
Yep. You can finish it, Stuart.
no, don't worry. I was looking at it incorrectly.
Okay. The metal, in this case it was magnesium, but it could have been anything that would react with hydrochloric acid. So the metal is oxidized and the...
Acid is reduced.
Yeah, but we don't want to call it the acid.
Oh,
What is this?
Solution.
The hydrogen ions. You have to say, you've got to be very specific about the species because that's hydrogen. This is hydrogen ions.
okay.
The hydrogen ions are reduced. So that's your answer. Your answer would be, I'll read out mine. Where have I put it? Anyway, something like that exactly. I said H plus ions from the acid are reduced. The metal loses electrons and is oxidized. And you can see that I could add those two together to get a net ionic equation that would not include the spectator chlorine. And the 2 electrons would cancel on both sides. Okay. That's why I'm only picking the very few necessary ones because there's a lot of concepts covered in one question. That did cover a lot just in that question. So the next one I think we'll skip for the time being. It's a different term altogether. I don't want to confuse you. So we'll go over that maybe later stage. Looking at 4, consider the following reaction. I'll go through that with you because you'll be good at this by now. I'll do a different colour. So on your sheet, question 4, it says, have a look at this reaction. So it's magnesium, solid. It's being burnt. So if you're in a normal face-to-face school, in a lab, one of the favourite experiments is to get a strip of magnesium and to burn it in the Bunsen. It goes really a bright white light. It's so bright that you have to wear dark glasses, special polarized dark glasses, otherwise it burns the back of your retina and it can do, and it can cause sight damage. So students love this because you burn the magnesium, which is a metal, in the hottest part of the flame. It burns really brightly and the end result is a magnesium oxide powder, which is white. It's a fine dust. That's all that's left. So this is a common reaction. You can see it's balanced. It's a redox reaction though, and so what the question is asking you to do, well, in an exam they might ask you, is this a redox reaction? And you have to determine whether it is or not. Are things changing state by gaining electrons and losing them? So in this one it's telling you it is. Identify the species that's being oxidized. What do you think?
Magnesium.
Magnesium. Do you want to come up and have a go at writing the Huff equation?
Yeah.
Great. Excellent. You can use whatever colour you like, actually.
Oh, wait.
So you split it back up into its ions because this is a compound. So this, even though it's a solid, you can split it back up into its ions. So do that. Do you know what the Mg is in group 2? Yeah, that's right.
And then
Yep. Yes. That's what. Which one is that? Oxidation or reduction?
yeah.
Excellent. Beautiful. And then the reduction. I might be out of a job.
Wait.
O2, yep. Start with this species. And then leave space, because, or it doesn't matter, you can add it here. So you draw your arrow, and then this is an ion. Do you know what the valency of oxygen is? It's in group, would it be 6?
2 minus.
Yes, group 6, 2 minus.
And then,
You've just got to balance the charge.
wait. Did I go on that side?
Well, if you put electrons on this side, it'd be even more negative.
Yeah. Then you have to go. I think.
Yes, and then what is that? Oh, very good. Yes. So, now that you've done that, and that's very good, you need to identify the species. So, the species that is oxidized is magnesium metal, or you can say magnesium solid, but you need to say what state it's in. And the species, see how it says the word species, that's being reduced, is the oxygen gas. And then it asks you to write the 2 half equations or 2 half reactions, and you've done that. So you've answered that question. Really good. Very, very good. So the final ones that we're going to do is this one with the periodic table. So take in your, I've given you a periodic table, this one, and this is, you should be able to do this. This is basic knowledge of periodic tables and the reactivity of metals. So it says use the information we've been talking about on the periodic table below, identify on the periodic table below, so this question here, where the most active and least active metals are located. But you should already know that. That's the general information. So I'll just help you recall. Do remember that this step ladder line here splits up the periodic table into 2 groups. Do you know what 2 groups?
Metals and non-metals.
Yes, so it's amazing that most of the elements known to us on this earth are metals, and only this top little corner here are the non-metals. So most of it's metals. Now, so we're only interested in the metals. We want to say where the most reactive metals are and the least reactive metals are. So in general, it does vary with individuals, but in general, where is the most reactive metals?
On the left-hand side?
Absolutely. So group 1, so the columns are called groups. Group 1 are the explosive metals. In fact, another favourite demonstration that you do as a teacher is you get sodium metal. Sodium metal is very unstable in air and in water, particularly in water, and it explodes. And so when you get it out, it's kept under liquid paraffin wax, and you take it out, and as soon as it gets into the air, it starts reacting. So you've got to move quite fast. So you take it out. It's still got a coating of paraffin wax on the outside from bringing it out of the liquid paraffin, so it's all right. And then first of all, you show them that these metals are really soft. You can cut them with a butter knife, and when you do, and it falls over, the inside looks like it's been hacksawed. It looks like a metal that's been hacksawed because it has a metal colour, sheen, everything, but it's soft like butter. And then you throw a small piece, and that's where some teachers have come into strife, I mean the size of a pea, into some water, and most of the energy is sound. It goes bang, really loud. In fact, I've done it at school and everyone thought it was lockdown. People have gone, lockdown procedures, and gone into panic because I've forgotten to tell the office that I was doing this demonstration with sodium. So, and also a big cloud of smoke comes up and flame, but mainly it's sound. So all of these metals are that reactive in water. And as you go down the column, they get more and more reactive. These ones are radioactive down here. So they're the most reactive. The second column, magnesium, very reactive, but not as reactive, not explosively reactive. So we can have magnesium ribbon in our hand and not be burning. If you tried to steal, like some boy in one of my classes did, tried to steal some sodium, it will burn a hole in your hand and in your pocket, and it scalds. It's very dangerous. All of these metals are very reactive. Most reactive, second most reactive. The most unreactive metals are in the transition elements, and you probably know there's things called noble metals. What haven't I used? Red. The noble metals, like the noble gases. Noble gases are these ones in the last group. You know that. The noble gases are unreactive, and they don't react with other species. So helium gas, for example, it's monatomic. It floats around as one atom of helium. It doesn't react with anything. Helium balloons. They're called the noble gases. The noble metals are reactive, but they take thousands of years. So we use them as jewellery. So what do you think?
Gold.
Gold? What's the symbol for gold? AU. You wouldn't pick that, would you? It's Latin or something. So you have to try and remember. Have a look where it is. Here. Gold. And you have to know its valency. And I was telling the students yesterday that some of these you've got to learn off by heart. Gold has +1. What's another one? Jewellery.
Silver.
Silver. Symbol?
AG.
AG. And it is +1 as well. And you can see where it is. It's in this group here of the transition elements. And what's another one? Platinum, PT. And not so much, but still sometimes called a noble metal, is copper, because it's very unreactive. Copper. It depends. I've seen in textbooks just these three because they really are very slow to react, thousands of years. This one will react, you know, it goes green. It does oxidize, but it is very unreactive as well, so sometimes they include copper. So you can see their location, they're all together, aren't they? They're the most unreactive metals in that, and you can identify that. So they're called the noble metals. All right. And then, we're almost there. We've got 2 more questions if you're getting a little bit weary. If you have a look at question 10, this is like what you'll be doing this afternoon. Here is someone's experiment. You can see that on the top going across there's a number of different metals, and on the side is what they've put these metals into. So part of the skills in chemistry and also in maths, physics, biology is being able to decipher secondary information, secondary data. So you should be able to look at that table and understand what it's saying. So firstly, it asks the general question, what is the colourless gas being formed? So we've got a metal going into an acid. Was that a general rule? Yes. What type of gas forms?
Hydrogen.
Hydrogen. So that's just testing your general knowledge. You can see how important these rules are, and I'll write them for you along with those polyatomic ions to learn. So acid plus metal gives salt plus hydrogen. It's odourless gas, hydrogen, but very explosive. B, use the results in the table to arrange the metals into 3 groups: highly reactive, moderately reactive, and non-reactive. So do you think you can do that for me? By those ticks. I'll give you a couple of minutes, or 1 minute. So, what do we say? Which ones were highly reactive? Let's ask Paige.
Lithium, calcium.
And that's it, yeah. How could you tell?
Because they're further away on the
But from this data, how could you tell?
Both the ticks are.
So that this table shows that both lithium and calcium react with water and acid, because mostly they will ask, explain your reasonings. They haven't on this question, but in an exam they would say, explain your reasoning. And you'd have to say, lithium and calcium both react with water and hydrochloric acid. And then it says moderately reactive. I have a hard time saying that one. What do you think, Stuart? Which ones?
Iron and zinc, due to the fact that they've only reacted one of them.
Yes.
Comparatively.
Only the most reactive metals can react with water. Moderately reactive metals can react with acid. So that's right. They've got a cross for water and a tick for acid, so it's iron and, what was the other one you said?
Zinc.
Iron and zinc are moderately reactive, and then you have the non-reactive. Sam, what did you say?
Silver and copper.
Silver and copper, which happen to be noble metals. Yes, so that's right. Very good. And the last part of that says, if there is more than one metal in each of the categories, moderately reactive and non-reactive, suggests an investigation you could do to distinguish between their reactivities. Now this is based on what I was telling you with those pictures of beakers and metals before. What could you do? So if I wanted to find out, for example, out of iron and zinc, which one was more reactive, what could I do? Remember the other side of this board. What could you do?
You could have like the aqueous solution of two of the metals, or one of the metal, and would it be hydrogen or something?
No, but you're close. You're very close. What you could do is use red. Just use this box over here. What you could do is a beaker, and we're trying to work out what's more reactive out of zinc and iron. So you get some iron sulfate solution, FeSO4, or we know that you missed this yesterday, Sam, but all nitrates are soluble. So you could use iron nitrate solution because you know it's soluble. Then you've got your ions in here, and then you could drop a piece of zinc in. Now tell me the rule. If a reaction occurs, what does that tell you?
The zinc is more reactive.
Yes, the zinc is more reactive. And if no reaction occurred,
The iron is more reactive.
yes, so that's what you would write in there. This. So you would set up that. This is called a galvanic cell. Well, I don't know whether you can actually read that. Let me start again. A galvanic cell. And that is that. And then, after you've written that, the very last thing I want you to look at is that cartoon. Because the cartoon, this cartoon, is only understood by chemists. It is very specific to people who study chemistry. Otherwise they wouldn't get it. So that's what's good about that. And I want to see whether you can now understand what's happening there. So it shows a piece of silver floating around in, what does that bottle say there?
Copper sulfate.
Copper sulfate. And he's happy, isn't he? He's going la 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 in the blue liquid, but the magnesium is climbing the ladder and just about to jump in, and he says, activity series, I've never heard of it. So what's going to happen?
It's going to be a reaction.
What's going to happen to magnesium?
It's dissolved.
It's going to dissolve. And why doesn't the silver care?
Because it's not reactive.
It's less reactive than copper. Less reactive. So it's floating around in there, no reaction occurs. Copper must be more reactive than silver, but magnesium is definitely more reactive, as you can tell by the position on the periodic table. definitely more reactive than copper, so it's going to dissolve. And that's why only a chemist would laugh at that and go, haha, that's funny. And a bit cheesy. And with that, we can finish. Hooray!